you can.
Yes, your
yes,
screen.
okay, great.
Perfect. You
right.
can stop.
Yes, let me just see how to put it in play now that I have the other one in front. Oh. I can see the button, but the menu is in the front. Okay, there. Okay, great. So my name is Enrique Moreno. I will be talking to you today a little bit about what goes on before all this other stuff. So I'm interested more in the part of central engines and how to get to form them. So one of the interesting things that you need to do that is to get the two stars together to form a GRB. So what I'll be discussing is how do you form, or how do you get these two stars together through a common envelope. And when you get a common envelope, you probably have to get an accretion disk formed around a compact object, and also launch jets during, or you could launch a jet during this stage. So I'll be studying a little bit of that, which is some work I have done with Fabio and Diego here, who also gave talks today. So let me go to the Outlook. So I'll talk a little bit about binaries and stuff like that for the introduction. Then I'll discuss common envelope, and then I will discuss the setup or our numerical setup for our experiments. And after that, I'll discuss jets during common envelope phases, and then I will conclude. So as we've seen recently in many studies, most stars are in binaries, and in particular, the ones we are interested on, which are massive stars, you have an even larger percentage, so around 71% of them. From you can see the paper from Sana et al. On this. So why do we need a common envelope? Well, as Fabio was mentioning in his talk, in order to produce a long GRB, we need to have a lot of energy that you don't seem to have available during typical supernovae. And one of the ways to do this is to use the kinetic energy from the orbit of two stars to tap this extra energy and produce this extra energetic phenomena, which are long GRBs. Also, for short GRBs, you need to have two stars in a very tight orbit, and of course for gravitational waves, kilonova, and also in order to produce the R process nucleosynthesis, which gives us the heaviest elements. This is necessary. So how do you come about to produce this sort of thing? And let me just remark, our process, we've seen now that this occurs in short GRBs with this 170817, but there's also there are also studies that show that during the collapse of massive stars, when you get a collapsar or long GRBs, you can also produce this R process. So both of these channels require this, or seem to require this binarity. So, but the stars that give you these are very massive, very big stars, usually a few tenths of solar radii in diameter. And one can see that in order to merge or bring close together these massive compact objects, you need to have, as you can see in the equation at the bottom, orbits which are not much more than a few tenths of solar radii if you want to have the two objects merge within a Hubble timescale. And in fact, most of the, in particular, short GRBs that we see are much closer. They're not necessarily far away. They're not cosmological, like long GRBs. So you would need even closer stars or orbits in order to produce these things. So how do you get stars which are tenths of solar radii into orbits which are just a few solar radii, or in some cases, for example, the neutron stars that we have, the double neutron stars that we have observed in our galaxy are within just a solar radii? in the case of long GRBs, for example, you may need final orbits before the collapse of the star. The orbit may need to be 1, maybe 2 days in order to be able to transfer enough angular momentum, enough energy to produce these collapsers. So how do you get there? Well, the answer is, well, if you have a binary, you can have that one of the two stars, let's say the more massive one, evolves faster, becomes a red giant or a red supergiant, and starts transferring material from the star to the companion. So Roche-Lobe overflow can help you if you are transferring mass from the more massive star to the least massive star. You can shorten the orbital period. So what we want to test now is what happens when this goes into an extreme case, when you have I forgot the word. Well, when the mass transfer is unstable, then you can have a runaway, that's the word, a runaway process that brings the massive star not only to fill its Roche-Lobe, but to fill also the Roche-Lobe of the companion. So both stellar nuclei share the envelope. So that, of course, can shorten the orbit and bring the two stars very close together. So during the common envelope, we may have lots of processes going on. It is not very well understood. It's a not well understood process, and many things can happen, as I was saying. One of these is you could launch jets and help remove the envelope with this process. So that's what we've been studying. Basically, what we did was take Fabio's mescal code, which is a 3D Eulerian adaptive mesh refinement code. In this case, our mesh is a few times 10 to the 12 centimeters per side, the cubes where we have our simulation. And we have a resolution of about a few times 10 to the 9 centimeters. So what we did is we took a compact object, be it a black hole of 5 solar masses or a neutron star of 1.5 solar masses. We put it inside a medium which is similar to the envelope of a red giant. In this case, we're taking a model from Papish et al. From 2015, which has this density profile of the power of the distance to the minus 2.7. And we choose a wind velocity, which of course, if the stars had been tidally synchronized, would be 0. But to make things interesting, we can choose to have non-orbital, not tidally synchronized. So then the wind that comes into the black hole will have the Keplerian velocity, which is a few hundreds of kilometers per second. Of course, if we had the synchronized case where the velocity is 0, we would just simply have Bondi accretion, that is spherically symmetric accretion, which would be limited to Eddington accretion. When we don't have this tidal synchronization, then we have these hundreds of kilometers per second wind, and what we get is Bondi-Hoyle Littleton accretion plus the density and the velocity gradients. So it's not exactly Bondi-Hoyle Littleton, but then we break the spherical symmetry and we may accrete much more than Eddington or over the Eddington. So what do we expect? Well, here I'm showing you a pressure versus radius plot. And you can see that the upper part is dominated by the pressure of the jet. So if the jet has a lot of luminosity, the jet will simply blow out of the common level. If the jet is not so powerful, then you could have that the dynamics of the jet are dominated by the wind, so the incoming material from the common envelope, or it could even be dominated by the infalling material, which is the pressure A or sub A that you have at the bottom, in which case the jet may even be quenched. So let's see in 2017, we published our first study. Let me play the two at the same time. The one on the left basically is just launching the jet without caring what's going on before. We can see that the jet comes out and it's slightly tilted to the left by the wind. However, on the one on the right, we can see what we are doing there is we're allowing for a steady solution. So the wind comes in, it starts forming this Bondi-Hoyle-Littleton bulge behind the accretor, and finally we launch the jet after a little while. And we can see that the jet has to come out from this bulge, which is actually the densest part. So it looks for the region where there's least density and least resistance. So it tilts a little bit forward onto the wind, and it finally comes out. In this case, we have a very powerful jet, so it has no problem getting out. So basically, our prediction or our analytic result seems to be correct. We have that if the jet is very, very powerful with large efficiency, the jet is simply launched. And you can see that the cocoon looks like it gets much faster to the equatorial plane, which is the bottom pane, on the right side than on the left side, because on the left side you have the bulge with large density, so it prevents the cocoon from expanding rapidly in that direction. Then on the left side, you have the deformed jet by the wind. So when the jet is not as luminous, then you get these effects of the wind. And on the bottom, you can see that if the efficiency is not too low, the jet is quenched simply by the accretion flow inside the Bondi-Hoyle-Littleton bulge. So we decided to go forward and we did an extra or a next paper trying to figure out, well, as we saw here, especially on the right top, you can see that the cocoon gets into the equatorial plane, so as to prevent material from falling in. So this could quench the jet after the material in the accretion stops flowing in. So could it be that the jet kills itself by its cocoon by not allowing more material to come in? So we decided to test
you have
it.
2 minutes.
Yes, thank you. And we did with different efficiencies. You have now a new definition of efficiency. Now it's the accreted mass against the ejected mass. And with different efficiencies, you can see that the jets can actually come out. They can be affected by the wind. These are not very, very efficient, especially the one on the right. But it looks like there's some sort of feedback between the jet, which produces a cocoon, stops the inflow, but that stops the jet, so more material accretes, which produces a new jet. So you get this balance between producing and quenching the jets. So it still seems to work, although now it's modulated by this negative jet feedback. We also tried, instead of putting a black hole there, we can see this one with a neutron star. This one has a large efficiency of about 10%. The jet has no problem coming out with such a large efficiency, but this being a smaller creature has less luminosity, and the jet still gets pushed around by the wind. So after this success, we decided to test a few other things that we had neglected in our first studies. One of them was what happens if the compact object is not it's spinning but not aligned with the orbital plane. Then the jet may be directed in different arbitrary directions. Other things which we had not included in our models before were Coriolis and centrifugal forces, so we decided to include those, especially because we also were interested no longer just in the accretion, but on whether you could form an accretion disk to produce the jet. I mean, we were supposing they were formed, but we had not tried to analyze whether this was the case. So on the left side, you can see a jet which is launched 45 degrees against the wind. and on the right-hand side, one which is thrown backwards. Let me replay these movies for you. So the one on the right, pushed against the wind, it comes out in the direction of least resistance, and the jet eventually gets blown by the wind and by the lack of accretion, and it accretes again, and it comes out again. Nice. The one on the right-hand side, we're trying to throw the jet backwards, so with the wind, but you can see that it has to look for the direction of least resistance, and that's going forwards, actually. So it has to blow away the Bondijoy-Littleton bulge before it can actually launch. It's always being launched backwards, but at the beginning, it seemed like it was being launched forward just because of this region of high density behind it. So this seemed to produce slightly different morphologies in the jets, but actually the accretion rates will be similar, as I'll show you in a minute. And the other thing which we were worried about, as I mentioned, was whether disks were being formed. So this is a close-up to the central region. The purple circle you see at the center is the region where our domain ends, but that's where, so this is about 1 solar radius. It's around 10 to the 11 centimeters. The black hole would be at the center, or the neutron star in this case would be at the center. And what we're plotting here in different colors are the angular momentum velocities. And you can see that if you get to the orange and red regions, you're basically reaching Keplerian velocities at 10 to the 11 centimeters. So let me play this and show you. You can see that a ring is starting to form there. So even if the material does not form an accretion disk perfectly well defined over there, you can see that it will definitely not fall inwards directly towards the compact object, but will form. Sorry?
Can you
Yeah. So here's another, the other model that I was showing you. So this is just the equatorial plane, and you can see that disks are starting to form around there. So just to finish, these are about the 10 models that we tried with different inclination angles, different efficiencies. You can see that the accretion is around 10 to the 25 grams per second. So if you translate that to solar masses per year, we are in a few tenths of solar mass per year. So we are definitely above Eddington limit. And on the right-hand side, you can see different plots for our different models of the angular momentum that we're having. The spikes that you see going towards the bottom are just, we're plotting the absolute value of the angular momentum. So you will have flips in the direction of, so you will have different rings with different orientation of angular momentum. So my conclusions are these: jets which are producing common envelopes play a crucial part in binary evolution. Lacking the jets, but still having this Bondijoy-Littleton accretion will still give you a hypercritical accretion. We can establish even the efficiency necessary for accretion of the jet to traverse the envelope. Definitely the negative jet feedback is an important part of this process. Also, energy deposition by the jets is comparable to the orbital dissipation, so these will help to close the gap between the two stars and bring you with much closer objects that will eventually merge. And well, efficient jets, which are launched from very deep inside a massive star, could definitely give you some sort of like a loop, ultra long GRBs with these very tenuous ones, but very long. And the nice thing is disks are formed, so this is consistent with launching jets.
Very long.
Thank
you. Okay, so thank you, Enrique. We have time for only one question. From Gerardo, can your models explain ultra-long GRBs?
Yes. So in principle, yes, we could form if you manage to get the compact object fairly close to the core, or even within the core of the star, where the accretion of much more denser material occurs, you could definitely have something like these very, very long GRBs.
Okay, thank you.
Thank you.
Thank you, Enrique. Of course, if you have other questions,